the Alexander cell and the scientific measurement of energy. This video explores a fundamental idea, the measurement of energy and the scientific tipping point represented by the Alexander cell. Everything in the universe depends on energy. Every system, from the largest structures to the smallest electronic devices, relies on the movement and control of energy. Understanding this requires measurement, and the history of science can be seen as a progression towards measuring energy more precisely. The evolution of electronics reflects this journey. Early systems used large valves and operated with relatively high voltages and currents. Over time, these systems developed into transistor-based technologies, becoming smaller, faster, and more efficient. Measurements moved from volts and amps to microvolts and microamps, and from seconds to milliseconds and nanoseconds. Physical dimensions reduced from miles and inches to millimeters and nanometers. As systems became smaller and more precise, measurement itself became more difficult. At extremely small scales, the act of measurement can influence the value. This often is described using the term quantum, where observing a system affects its value. So you look at something, and by looking at it, you have reduced the value. To manage this complexity, modern technology relies on software. Software is a set of instructions that controls electronic circuits. Computers, at their core, are machines that process electrical signals using binary logic. These signals are organized into sequences of operations known as algorithms. Algorithms control how systems behave. They manage communication, processing, automation, and decision-making. They are essential to modern infrastructure, from financial systems to communication networks and advanced technologies. However, all of these systems depend on a reliable supply of energy. Electronic processes requires electrical power, and this power is provided by batteries. A battery is fundamentally an electrochemical system based on corrosion reactions. These reactions generate the electricity required to drive electronic circuits and enable the execution of algorithms. Without this energy, no system can function. Without accurate and stable energy supply, systems become unreliable. This leads to a critical point. If energy is the foundation of all electronic systems, then the ability to measure that energy accurately is essential. This is where the Alexander cell becomes important. The Alexander cell provides a method of measuring real electrochemical activity. It measures actual corrosion current, which represents the movement of energy at the interface between metal and environment. Unlike indirect measurement techniques, it captures real behaviour, not theoretical balance. This allows us to observe energy at its source. It provides a direct link between electrochemical processes and measurable electrical activity. It bridges the gap between theory and reality, allowing energy to be understood in practical terms. As electronic systems continue to become smaller and more precise, the importance of accurate measurement increases. At very small scales, where individual electron behaviour becomes significant, reliable measurement methods are essential. The Alexander cell contributes to this understanding by providing a clear and measurable representation of electrochemical energy. In this way, it represents a step forward in how we observe and understand energy in real systems. It allows us to move from assumption to measurement, from theory to observation, and from uncertainty to clarity. Understanding energy is fundamental to understanding the systems we depend on, and the ability to measure its accuracy is where that understanding begins.